So let's start kind of big picture. There is the equilibrium constant Kq, which is a numerical value for what the ratio between the concentration of the products and the reaction should be at equilibrium. And this Kq is established by a thermodynamic property, specifically the delta G, the Gibbs free energy change. So Kq is the most generic expression out there. Any equilibrium constant has a Keq value associated with it. But because there's so many specialized and common equilibrium reactions, we actually have a subset of equilibrium constants that has special letters to describe them. So while you can say Keq for any number, when we start talking about these particular equilibrium constants, we're talking about a specific type of reaction. So the first we're going to talk about is Ka. Now Ka is the equilibrium constant for any weak acid dissociation. So this will be Ha, Aq, going reversibly back and forth to H plus, Aq, and A minus, Aq. So whenever we say Ka, we are implying that we have an acid that is going to deprotonate to give us an H plus and an A minus. So if I give you a reaction to say this is the Ka of HF, you should know that HF is going to dissociate into H plus and F minus. Now, the sister of this is the Kb. And with Kb, this is the weak acid, this is the weak base dissociation constant. Now, a caveat on this. There are actually two types of weak bases. There are Arrhenius bases and there are Bronsted bases. So your Arrhenius base is going to have the OH minus in it and it's going to give it up to give you, the conjugate acid plus the OH minus. The Bronsted is our proton acceptor form. So for the Bronsted definition, we have our base, B, plus water, goes back and forth to BH plus AQ plus OH minus AQ. This is one form of Kb, and honestly it's the most common because typically when we're talking about Arrhenius bases, we're talking about strong bases. The only definition of base you really need to know is this Bronsted definition, but there are a few weak Arrhenius bases out there, and they would have their equilibrium constant BOH AQ goes back and forth to B plus AQ plus OH minus AQ. But again, when we're talking about Kb, we're typically talking about this. So if I say, well, here's the weak base and it's Kb, you should know that it's taking a proton from water to give you OH minus and the conjugate acid. Another equilibrium constant, Kw. This is a very important equilibrium constant. Kw is the auto-dissociation water equilibrium constant. So H2O goes back and forth to H plus AQ plus OH minus AQ. Now, this is one definition of Kw. There's actually a second. And the second definition is 2H2O goes back and forth to H3O plus AQ plus OH minus AQ. Now, typically we almost exclusively work with this definition. So why does this definition exist? Well, there are a few professors out there, and there is some legitimacy to this claim that say that H plus can't exist by itself in water. If you look at what hydrogen is, if it's H plus, it's a lone proton floating in water. And they say that's not really what happens. What really happens is you form the hydronium ion H3O plus. So some will advocate that this is actually what Kw is because you can't form H plus. Now, that said, I only teach this one. And the only reason I teach this one is if you look at pH scales, it assumes that you're forming protons in water. It's nitpicking, there is justification both ways, but honestly, if you're looking for efficiency, this is the only definition of Kw you need to memorize. Now, another one, very important one, is the solubility product Ksp. Now, unfortunately, Ksp does not have a universal form, meaning with all these, we can sit back and say, well, this is definitely what the reaction is going to be, we just have to fill in the blanks. Well, Ksp is a bit more complicated. Ksp is the equilibrium constant for a semi-soluble salt. So we're going to have some salt that's a solid dissociating back into cations, AQ, plus anions, AQ. Now, the big thing about Ksp, this is the net ionic equation for the salt's dissociation. So if we have something like calcium phosphate, PO4, we're going to break it completely apart. When we finish, it will only be positive ions and negative ions. There won't be any pairings of them. So we'll have 3Ca plus 2AQ plus 2PO4 minus 3AQ. Now, The reason I had to make this stipulation is that not all materials do this. There are some things that only partially dissociate in water. Now, I can't really find any examples for you. I had to go dig back through a bunch of old chemistry books. But there are some materials where only one of the anions pops off. So maybe it's something like, I'm guessing here, calcium bicarbonate. Maybe this doesn't completely split up. Again, I don't know if this really happens, but this would be an example if it did happen. It doesn't completely dissociate. The solid here kind of breaks into part of the ions. When we're talking about KSP, we're talking about the complete dissociation, the net ionic for the salt dissociating. But this will always be the reaction. We always get the salt completely decomposing into its cations and anions. So if you're ever asked about the solubility of a semi-soluble salt, or you're given salt and you're asked how much of it dissolves, you're working with the KSP problem. So these are the different types of equilibrium constants you can have. That's what they describe. So next videos, let's talk about how to actually be quantitative and find basically concentrations or values using this information.